Greetings everyone, this is CMA Nishanth Reghunath here, welcoming you to a new video under my study for operations management. And as you can see right here on your screen, the topic that we are going to discuss today is queuing theory. It's also referred to as queuing models or waiting line models. So from the name itself, it's pretty evident. It is a study about queues, yeah? So it's a mathematical study about queues wherein we use a lot of mathematical formulas to efficiently manage a system of queues. And what is a queue? Queue is nothing but a waiting line. For example, a line of people waiting at a ticket counter, yeah? That's a queue, right? So to understand this whole concept of queuing theory, we need to know certain concepts first. So let's take this diagram and I'll give you an example out of the diagram. So these dashes that you see, that is a queue. Queue of people waiting to get tickets from a ticket counter. Let this box be a ticket counter. So they are at a movie theater, people waiting in a queue to get tickets from this ticket counter. This ticket counter, that is the place, the point wherein the people in queue are waiting to be served, is called a server. So in our example, the ticket counter, the person issuing the tickets is a server. Alright. So we have a queue and a server, and this whole area, the whole area including the queue and the server, is called a system. Alright. And queuing theory is nothing but a mathematical study to efficiently manage a system. System comprises of the queue, the customers, and the server or the service center. Alright, so that's what queuing theory is. Got it? So understood a basic definition, or did you get a basic understanding of what the whole concept of queuing theory is? Yeah? Fine. So in order to study queuing theory in depth, we need to learn certain concepts in detail. Concepts such as, number one, customers and the queue that they form. Their arrival, how they arrive to the queue. Number two, the servers, yeah, and their service rates. Alright. Number three is something with regards to this queue, that is the queue structure, the queue structure. And number four is the system structure. So these are some of the very important things that you need to know before learning queuing theory. So let's start off with system structure first. See, in the diagram that I showed you previously, in this diagram, we just have a single queue and a single server, right? Single queue and a single server. That is a single server facility. A single server or single service facility. So we have, under different systems of structures, we have one single service facility wherein there is one queue and there is one server. Alright. After single service facility, we have a multiple or parallel facility with single queue. Multiple facility with single queue. I'll explain what it is. A multiple facility with single queue is a facility wherein there will only be one queue for customers to wait. But after they reach the server or after they reach the service station, they can go to three places of their choice. Any of the three places, which one is vacant, based on whichever one is vacant. So if we have three people coming in, one person can go to the server 1, one person can go to server 2, another person can go to server 3. So at times 3 people can be served in this example, but then people will wait in a single queue, that is multiple or parallel facilities with single queue. Now another system of queue is multiple facility itself, but with multiple queues. That is a facility wherein there will be multiple service stations, and each of the server or service stations will have their own queue. For example, you will find such systems at say a motor vehicle service center. When you go to deliver your scooter or two-wheeler for service, you will see that at service booking area there will be at least 3 to 4 service booking areas, and for all those 4 booking service areas they'll have separate queues. So we get into whichever lane which has less number of vehicles, right? So that is an example of multiple facility, multiple service facility with multiple queues, right? Yeah. And then we have another peculiar, unique queuing structure called series facility or service facility in a series. Service facility in a series. Now what is this? This is nothing but, say let's just take this system, the one that we are seeing below. Alright, this system for example. So people stand in a queue, or whatever activity or whatever item is waiting to be served is waiting in a queue. They get served at server 1. Now they form another queue and enter server 2 for another service. Then again they go on a queue, enter server 3, and finally get served by server 3 and leave the system. So this is service facility in a series. So these are different kinds of system structures. So now you know what are the different kinds of system structures. For queue also we have different structures. For example, first come first serve. First come first serve, FCFS. That is, a customer who comes first is served first. That's the general way or the most common way queues function all around. Next we have last come first serve. These are all queue structures. Alright, queue structures. Last come first serve. For example, you are working in an office and your subordinate brings a lot of files for you to check. Now the subordinate arranges all these files on your table one after the other. So the first file that he brings goes to the bottom of the whole list. On top comes the file that he brings next, and the last file that he brings will be on top of the rack. And generally you will take the file on top of the rack first, yeah? So that's a case where you serve the last item in queue. Last item which fell in queue. Then we have a special system called SIRO, service in random order. Here there is no such sequence, no order in which the service is to be conducted. The server comes and takes up to his wish. He takes whichever item he wants to serve as per his desire and services it, provides it with the service. And finally we have priority structure. Priority structure is where, regardless of the time or regardless of the order in which the customers came, the server will have a pre-decided priority. So say we have customers A, B, C, D, A, B, C, D, who comes to a service facility. So A comes first, B comes second, C comes third, and D comes fourth. Let this be a clinic, a hospital. So this is the order in which they arrived. A came first, B came second, C came third, D came fourth. But then they had already taken pre-bookings. That is, they had already set their bookings. So the hospital has a priority. Let the booking order be, the first booking was for C, second booking was for D, third booking for A, and fourth booking for B. So hospital already has set their priority. Hospital will serve C first as and when their serving time starts. Fine. That is a priority structure. So now we discussed systems structure and queue structure. Now what we have left to discuss is 1. Something with respect to the customers, and 2. Something with respect to the servers. With respect to customers, what we have to discuss is something regarding their arrival. How do customers arrive? How quick do customers arrive? For that, we have a very specific symbol or a very unique symbol to represent their arrival, and it's lambda. We use lambda to represent it, and lambda represents arrival rate of customers. Say 5 customers come every hour, 3 customers come every half an hour. For example, 5 customers per hour, or 10 customers per day, or 1 customer per 10 minutes. So it is a rate wherein the arrival of customers are mentioned with respect to a unit of time. Alright. Now with respect to the servers, we have this thing called service rate or server rate. That is, how many units can be served by a server per a unit of time, and it's represented by symbol called mu. This is rate of server. Rate of server. Say we are running a car wash, and at our car wash we have a service rate or a rate of service. It's also called service rate. We have a service rate of 10 cars per hour. Alright. Or we are running some other facility. We are running a clinic. So we have a server rate of 5 patients per 1 hour. Yeah. So server rate or service rate is nothing but a rate wherein the number of customers are expressed with respect to a unit of time, denoting the rate at which they can be served. So with respect to customers and the servers, we have 2 very important concepts. They are arrival rate and service rate. And it's based on these 2 items we work out all the formulas in queuing theory. And also do keep one thing in mind: for queuing theory to work, we always need mu to be greater than lambda. Rate of server should always be greater than lambda, else queuing theory will fail. For queuing theory to work, we need this to be always applicable. That is mu being greater than lambda. And also we have one more thing. If mu is the rate of service or service rate, 1 by mu is service time per customer. Say 10 cars can be serviced in 1 hour. So what time will it take for 1 car? 1 by 10th of an hour. Right. 1 by 10th of an hour. And what is 1 by 10th of an hour? Is 6 minutes. So every 6 minutes 1 car will be serviced. So service time per customer is 1 by mu. Mu is 10 cars per unit of time, or number of cars, number of customers per unit of time. 1 by mu is time taken for 1 customer. That's the difference. So please do keep that in mind. Mu and 1 by mu are totally different items. And one more thing that I would like to explain here is something with respect to their distributions. See, lambda, that is the arrival rate of customers, follow Poisson distribution. You do not have to go in detail to learn about what Poisson distribution is and all. Just keep this in mind because there are chances that this will be questioned in your 1 mark area, objective question area. And 1 by mu service time follows exponential distribution. These are two statistical measures. Alright, statistical terms. Also one more very important thing. Make sure before you start doing a question, make sure that lambda and mu are expressed in the same units. That is, if lambda is expressed in hour and mu is expressed in minutes, bring them to the same units. Either make both in hours or both in minutes. Alright, so lambda and mu should be in same units. So either make mu to the same unit of lambda or make lambda to the same units of mu. Then only start doing the formulas. So before heading into the formulas, let me explain certain terms that you will require to solve these formulas. Right. So the first two items, lambda and mu, we have already discussed, and these two items will be generally given in your questions. So these two items will be generally given in your questions, or at times you will not be given service rate, instead we will be given 1 by mu, but we can easily find mu from 1 by mu. So you'll find these two in questions, and it's from these two items we figure out all the rest of the items. So first item, R. R denotes number of customers being served. The next item, the symbol is called rho. Rho denotes the utilization factor or traffic intensity or system utilization. Next we have LS. LS denotes the length of system. Length of system is LS. It's also the average number of customers in a system. So if we have a system of a queue and a server, and there are a couple of customers inside the server as well. LS denotes the length of the whole system. Alright, this is LS. LQ is the length of queue. That is the average number of customers in queue. This is LQ. Alright, just the queue, not the customers inside the system, not the customers who are being served inside the system. Whereas in LS we have customers who are in the system being served. Next, WS, average waiting time in the system. So total time a customer spends in the system, that is by waiting in the queue and waiting while being served. WQ is waiting time in queue. So two items each for length and queue. Length of system, length of queue, waiting time for customer in system and waiting time for customer in queue. And finally we have 4 probabilities to learn. Probability number 1, which is denoted as P0, is probability that the system is free. That is, our system is not functioning. That is, we have no customers in the system. The fourth probability is a straight opposite. I'm not going to 2 and 3. Instead, I'm going to the fourth one right now. It is probability that the system is not free. That is, there is at least one customer in system. The first probability was there is no customer in system, not even one. Fourth probability is there is at least one customer in system. Probability number 2 is Pn. That is probability that there are n number of customers in the system. For example, probability that there are 15 customers in the system. Probability that there are 14, 20, 25 customers in the system. Probability number 3 is probability less than n. That is probability that less than n customers are there in system. That is probability less than 15 number of customers are there in system. Probability less than 20 customers are there in system. Probability less than 40 customers are there in system. So these are the things that we solve by using formulas. So we have formulas for everything from R to the last probability, and that's what we solve in queuing theory. So shall we check all these formulas out? Before heading into the formulas, I want to explain one more term, and that term is M. It denotes number of servers. See, in my study for system structure, we saw different kinds of system structures, right? One, a single service facility, then a facility where there are multiple servers with single queue, then multiple servers with multiple queues, yeah? So M denotes the number of servers that are there in a system. Alright, now let's head into the formulas, breaking down all items starting from R. So yes, let's check the formulas out. So here are the formulas, and even though I've started from LS, I would suggest you to write R as the first formula and rho as a second formula, and then follow LS, LQ, WS, WQ, PO, PN, P less than N and all. Okay. So what is R? R denotes the number of customers being served, and R is calculated by dividing lambda with mu. So lambda divided by mu is R. Okay. Rho denotes the system utilization or traffic intensity or utilization factor, and that is nothing but rho divided by m into mu. What is m? M is the number of servers, or m is the number of service channels. So now we know the formula for R and the formula for m. Formula for rho. Now go to LS, LQ, WS, WQ, PO, PN, P less than and extra. So LS, that is the length of the system, right? Average number of customers in the system is calculated by lambda divided by mu minus lambda. Lambda divided by mu minus lambda. LQ is nothing but LS into R. LS into R. LS is lambda divided by mu minus lambda. Yeah. And what is R? R is lambda divided by mu. So lambda into mu minus lambda into lambda divided by mu. What will we get? We'll get lambda square divided by mu into mu minus lambda. See, that's it. That's it. So that's the formula for average number of customers in Q. Right, LQ is lambda square divided by mu into mu minus lambda. Clear? This is the general formula for LQ. But there are cases where the service rate will be same throughout. Say you are running an automatic car wash facility, and regardless of the car that comes in, your automatic car wash facility takes 5 minutes exact to wash any car. Alright, so regardless of the car, your service rate is fixed. If the service rate is fixed, the formula for LQ will change. The formula for LQ will be lambda square divided by 2 mu into mu minus lambda. Because we have 2 here, because when our service rate is fixed, the time customers spend in a queue will be far more lesser. The average length of the queue will be far more lesser because it goes far more quickly or far more orderly. So if the service rate is fixed, then the formula for LQ is lambda square divided by 2 mu into mu minus lambda. Understood? Now let's go to WS. WS and WQ are nothing but the respective L's divided by a lambda. So for finding WS, take LS divided with lambda. For finding WQ, take LQ divided with lambda. Alright, so take LS divided by lambda, you get WS. So lambda is lambda divided by mu minus lambda. If you divide this whole item with lambda, what will happen? The numerator lambda will get cancelled off. So it will be 1 divided by mu minus lambda. I'll show you. Lambda divided by mu minus lambda whole divided by lambda. What will happen? This lambda will cancel off, this lambda will cancel off. We have 1 by mu minus lambda left. Yeah? So that is WS. Now for WQ, same thing. Take LQ, lambda square divided by mu into mu minus lambda. Divide this whole thing with lambda. What will happen? This lambda will get cancelled off and the square will get cancelled off. Yeah? So it will be lambda divided by mu into mu minus lambda. So if it's a fixed service time interval, what will happen? It will be lambda square into 2 mu into mu minus lambda divided by lambda. So what will happen? This lambda and the square will cut off and our result will be lambda divided by 2 mu into mu minus lambda. This is in case our server facility service rate is fixed. Alright. So we found out LS, LQ, WS and WQ. So the most important formulas are done. Now going to the remaining few probabilities. PO. PO denotes probability that our system is completely free. There is no customers in our system. And that's found out by subtracting R from 1. R denotes number of customers being served. And PO denotes probability that no customers are being served. So that is 1 minus lambda divided by mu. Alright, 1 minus r will give you PO. Next we have PN. That is probability that there are n customers in the system. That is probability 0 PO into lambda divided by mu raised to n. So if you are finding P15, it will be P0 into lambda divided by mu raised to 15. Simple. N is the number of customers. Then we have P less than n. So if you want to find the probability that our system will have less than 15 members, 15 customers, the formula is 1 minus lambda divided by mu raised to 15. So 1 minus lambda divided by mu raised to 15. Alright. So that's it. That's all the formulas that you need to know for queuing theory. And what you see right here, that is lambda following Poisson distribution and 1 by mu following exponential distribution, is something that I had already explained. Also do keep in mind, lambda and mu should have same units. If lambda is in R's, mu should be also expressed in terms of R's. Also, mu and 1 by mu are completely different items. I'll give an example to understand this whole concept better. Say we have an arrival rate of customers, lambda, at 16 customers every hour. Alright. And also we are told that it takes 3 minutes to serve one customer. So what is this 3 minutes per customer? See, 16 customer per 1 hour is nothing but the arrival rate. What about 3 minutes per customer? It is definitely not the service rate, right? What does it tell us? It tells us about the service time. It tells us the service time, and we also know service time is nothing but 1 by service rate. So we need to find mu. What do we have here? We have service time. What is service time? Service time is 1 by mu. So we have 1 by mu here. From that, can't we easily find mu? Yeah? But before finding mu, check this out. This is given in minutes. 1 by mu is given in minutes and lambda is given in hours. It's given in 2 different units. So while finding mu, we need to first convert 1 by mu into hours. We need to make it in the same units. So to make it in the same units, what do we have to do to convert minutes into hours? Divide by 60. So this 1 by mu can be expressed as 3 divided by 60 hours per customer. Right. That is 1 by 20 hours per customer. Right. So 1 by mu equals 1 by 20. Therefore, mu equals 20. So our mu is 20 customers per hour, per 1 hour. Right. Easy, right? You can also check this out logically. You can cross verify. It takes 3 minutes per 1 customer. So in 1 hour, how many customers can be served? 3 minutes for 1 customer. 1 hour is 60 minutes. 60 divided by 3, 20. 20 customers can be served in 1 hour. So once you find lambda and mu, head on to finding LS, LQ, WS, WQ, or the probabilities, whatever that you require. So that's it for this study wherein I explained the complete concept of queuing theory. I'm hoping you guys understood this very, very well. If you have any doubt, please feel free to reach out. We are here always to provide any sort of assistance that you would require to make your learning experience all the more better. So with that said, I'm winding up this video. See you in my next video. Till then, take care, stay safe, and goodbye.